For a long time, astronomers believed they understood the life cycle of galaxies reasonably well. Galaxies are born rich in gas. They form stars intensely for billions of years, and eventually they slow down, run out of fuel, and quietly fade into cosmic retirement. That story felt clean, logical, and almost comforting. But over the last few years, something deeply unsettling has emerged from deep space observations. We are now finding galaxies that should have died long ago, galaxies that by every known rule should be cold, quiet, and empty, yet somehow they are still there, still massive, and in some cases, still active. And the deeper scientists look, the stranger this problem becomes. This episode explores those galaxies, not hypotheticals, not science fiction, but real objects observed billions of light years away, forcing astronomers to rethink how galaxies live, age, and sometimes refuse to die. The expected fate of galaxies. In the modern understanding of cosmology, galaxies are shaped by a balance between gravity, gas, and time. Early in the universe, gas was abundant and conditions were chaotic, allowing galaxies to grow quickly and form stars at incredible rates. Over time, that gas gets used up or blown away by energetic events like supernovae and active black holes. As the fuel disappears, star formation slows down, and the galaxy becomes what astronomers call quenched, essentially dead in terms of new stellar birth. This framework works well for most galaxies in the nearby universe. Massive elliptical galaxies tend to be old and quiet. Smaller spiral galaxies often still form stars, but at a reduced pace. Everything fits neatly into a timeline where age and activity correlate, or at least, that was the assumption. Then, telescopes began to peer deeper into the universe, looking not just farther in space, but further back in time. And that is where the problem appeared. Astronomers started finding massive galaxies in the early universe that already looked old. These galaxies had somehow formed enormous amounts of stars very quickly, burned through their gas, and shut down far earlier than expected. According to previous models, they simply should not exist yet. At first, these discoveries were treated cautiously. Maybe the data was incomplete, maybe the distances were wrong, maybe dust was hiding ongoing star formation. But as observations improved, the pattern became impossible to ignore. The universe, it seemed, had produced fully grown, apparently dead galaxies when it was still very young. And that raised an uncomfortable question. If galaxies can age and die far earlier than predicted, how reliable is the entire timeline of cosmic evolution? Galaxies that age too fast. The launch of the James Webb Space Telescope dramatically escalated this mystery. With its ability to see infrared light from the early universe, Webb revealed galaxies forming stars at astonishing rates just a few 100 million years after the Big Bang. Even more unsettling, it found galaxies that already appeared massive, compact, and chemically evolved at a time when the universe was barely out of infancy. Some of these galaxies seem to have completed most of their star formation in an incredibly short window of time. They formed stars so rapidly that they exhausted their gas reservoirs almost immediately on cosmic timescales. Others appear to have had their star formation shut down by mechanisms scientists still struggle to fully explain, possibly involving supermassive black holes heating or ejecting gas before stars could continue forming. What makes this especially strange is that these galaxies do not look chaotic or half-finished. They look mature. Their stars show signs of aging. Their structures appear stable. In other words, they look like galaxies that should belong to a much older universe. This forces scientists into an uncomfortable position. Either galaxies can form and evolve far faster than current models allow, or something fundamental is missing from our understanding of early cosmic physics. Neither option is reassuring. One implies that decades of galaxy formation theory need serious revision. The other suggests there are physical processes at play that we have not yet identified. And the deeper astronomers look, the more these early dead galaxies appear not as rare anomalies, but as a population that may have been surprisingly common. The illusion of death. As strange as it sounds, the story becomes even more complicated when scientists look closer at what dead actually means. Some galaxies, once classified as fully quenched, have shown subtle signs of lingering activity, extremely faint star formation, unexpected gas reservoirs, or energy signatures that hint at processes still unfolding beneath the surface. In some cases, galaxies appear dead only because their star formation has dropped below what our instruments can easily detect. In others, star formation may have restarted after a long pause, triggered by mergers or the slow accretion of fresh gas from intergalactic space. This raises the possibility that galactic death is not always permanent, but sometimes a long, deceptive sleep. Yet, this explanation does not solve everything. Many galaxies truly do appear devoid of the raw materials needed to form new stars. They are compact, dense, and quiet in a way that suggests their evolutionary path was fundamentally different from what scientists expected. These galaxies did not gently fade. They burned fast, aged rapidly, and shut down with startling efficiency. This leads to a deeper realization. The universe may not follow a single orderly script for how galaxies grow old. Instead, there may be multiple evolutionary pathways, some violent and brief, others slow and extended. The galaxies we see today could be survivors of very different cosmic lifestyles, shaped by conditions that existed only briefly in the early universe. And if that is true, then our own galaxy's history may be far less typical than we once believed. What this means for the universe. The existence of galaxies that should have died long ago has consequences far beyond galaxy formation itself. These objects affect how scientists estimate the mass of the universe, how they interpret the growth of cosmic structure, and even how they understand dark matter and dark energy. If galaxies formed earlier and faster than expected, then the timeline of structure formation shifts. That ripple effect touches nearly every major cosmological model. It also complicates the interpretation of the cosmic background light, chemical evolution, and the distribution of matter on the largest scales. Perhaps most unsettling is what this says about prediction itself. Astronomy has always relied on patterns, averages, and gradual trends. These galaxies remind scientists that the universe is perfectly capable of taking shortcuts, producing extremes, and breaking expectations without warning. They also serve as a quiet warning. The universe we think we understand may only represent the survivors, the systems that followed stable paths. The early universe may have been filled with galaxies that lived fast and died young, leaving behind faint fossils that only now are coming into view. And as telescopes continue to push further back in time, there is a strong possibility that even stranger objects are waiting to be discovered, objects that will once again force us to rewrite what we think we know about how the universe grows up. Galaxies that should have died long ago are not just curiosities. They are reminders that the universe is under no obligation to match our expectations. Every time science feels confident, the cosmos finds a way to introduce doubt. And somewhere in the deep past, massive galaxies lived short, intense lives, burned through their fuel, and went quiet long before they were supposed to. The question now is not whether our models are incomplete, but how many more surprises are still hidden in the early universe, waiting for us to notice them.